Hi to everyone. I am Dr.N.PRABHA, Associate Professor of Chemistry, A.D.M. College for Women, Autonomous Nagapattinam. Today, I am going to discuss about the fundamental concepts of thermodynamics. This unit belongs to General Chemistry 4 in Semester 4 for 2nd BSc Chemistry students. What is meant by thermodynamics? Thermodynamics, a study of flow of heat of any other form of energy into or out of the system as it undergoes a physical or chemical transformation is called as thermodynamics. A studying and evaluating the flow of energy into or out of the system, it will be useful to consider changes in certain properties of the system. These properties include temperature, pressure, volume and concentration of the system. Measuring the changes in these properties from the initial state to final state that can provide information concerning changes in energy and related quantities such as heat and work. The three empirical law is for the thermodynamics. The study of thermodynamics is based on three broad generalizations derived from well-established experiment results. These generalizations are known as first, second and third law of thermodynamics. These laws have stood test of time and are independent of any theory of the atomic or molecular structure. The discussion of these laws will be subject of our study in the chapter of thermodynamics. What is the scope of thermodynamics? In the first one, most of the important laws of physical chemistry, including the Van 't Hoff law of lowering of vapor pressure, phase rule and the distribution law can be derived from the laws of thermodynamics. It tells whether a particular physical or chemical change can occur under a given set of conditions, that temperature, pressure and concentration. Third one, it also helps in predicting how far a physical or chemical change can proceed until the equilibrium conditions are established. Now, let us see what are the limitations of thermodynamics. And the thermodynamics is applicable to macroscopic systems consisting of matter in bulk and not in microscopic systems of individual atoms or molecules. It ignores the internal structure of atoms and molecules. The second one, thermodynamics does not bother about the time factor. That is, it does not tell anything regarding the rate of physical change or a chemical reaction. It is concerned only with the initial and final states of the system. Now, let us see the thermodynamic terms and the basic concepts. An important part of the study of the thermodynamics in a few terms and definitions which must be understood clearly. That is system, boundary and surroundings. First we see system. A system is a part of the universe which is under thermodynamic study, and the rest of the system in the universe is known as surroundings. That is, system means that a part of the universe. In a universe, the rest of the system, the other terms are the surroundings. The real or imaginary surface separating the system and surrounding is called as boundary. We take an example. In experimental work, a specific amount of one or more substances constitutes the system. Thus, 200 grams of water contained in a beaker constitute a thermodynamic system. A beaker and air in contact are the surroundings. Another one example, 1 mole of oxygen confined in a cylinder fitted with the piston is a thermodynamic system. A cylinder and a piston and all other objects outside the cylinder form the surroundings. Here, the boundary between the system, that is the system is an oxygen, and the surroundings are the cylinder and the piston is clearly defined. Now, let us see homogeneous and heterogeneous systems in thermodynamics. When a system is uniform throughout, it is called as homogeneous system. Homogeneous system means a system is uniform throughout the process. Example, a pure single solid, liquid or gas or mixture of gases and true solutions of solid in a liquid. In a homogeneous system is made up of one phase only. A phase is defined mechanically separable portion of a system. In a heterogeneous system is one which consists of two or more phases. In other words, it is not uniform throughout the process. Examples of heterogeneous systems are ice in contact with water, ice in contact with vapor. Here, ice, water and vapor constitute separate phases. Now, let us see the types of thermodynamic system. There are the three types of thermodynamic system depending on the nature of the boundary. That is, isolated system, closed system and open system. If the boundary is closed or sealed, no matter can pass through it. If the boundary is insulated, there is no energy can pass through it. First, let us see isolated system. When the boundary is both sealed and insulated, there is no interaction is possible with the surroundings. Therefore, isolated system is one that can transfer neither matter nor energy to the surroundings. Let us take one example. We consider a system 100 ml of water in contact with its vapor in a closed vessel which is insulated. Since the vessel is sealed, no water vapor can escape from it and also no heat energy can escape with the surroundings. A substance, say as a boiling water contained in a thermoflask, is another example of isolated system. The next one is closed system. Here the boundary is sealed but not insulated. Therefore, a closed system in one which cannot transfer matter but can transfer energy in the form of heat, work and radiation to the surroundings. A specific quantity of hot water contained in a sealed tube is an example for closed system. While no water vapor can escape from the surroundings, it can transfer heat through the walls of the tube to the surroundings. Another one example, a gas contained in a cylinder fitted with the piston constituted a closed system. As the piston is raised, the gas expands and transfers heat energy in the form of work to the surroundings. Another one is the open system. In a system, boundary is open and it is uninsulated. Therefore, an open system in one which can transfer both energy and matter to the surroundings. For example, hot water contained in a beaker that is placed in laboratory table is an open system. The water vapor and also heat is transferred to the surroundings through the imaginary boundary. Another one example, zinc granules. Zinc granules reacted with dilute hydrochloric acid to produce hydrogen gas in a beaker is also example for the open system. Hydrogen gas escapes, the heat of the reaction is transferred to the surroundings. Next we see the intensive and the extensive properties of the thermodynamics. The macroscopic or bulk properties of a system, that is volume, pressure, mass, etc., can be divided into two classes. One is intensive property and another one is extensive property. First we see what is meant by intensive property. A property which does not depend on the quantity of a matter present in the system is known as a intensive property. Example for the intensive properties are pressure, temperature, density, boiling point, freezing point, surface tension, refractive index, viscosity and concentration. And extensive properties are the property does depend on the quantity of matter present in the system is an extensive property. Example for the extensive property are volume, number of moles, enthalpy, entropy and Gibbs free energy. In the both definitions, extensive properties are additive while intensive properties are not additive. Let us consider a system, a glass of water. If we have double the mass of water, volume is doubled and so the number of moles and the internal energy of the system becomes as a double. Now let us see the state of a system. A thermodynamic system is said to be a certain state with all its properties fixed. That is the fundamental property which determine the state of a system or pressure, temperature, volume, mass and composition. Since a change in the magnitude of such properties alters the state of a system, these are referred to as state variables or state functions or thermodynamic parameters. It also stands to reason that a change of system from the initial state to the final state will be accompanied by change in the state variables. It is not necessary to state all the properties to define a system completely. For a pure gas, the composition is fixed automatically as it is 10%. A remaining state variables, pressure, volume, temperature are interrelated in the form of an algebraic relationship called the equation of state. Thus, for 1 mole of pure gas, the equation of state is PV is equal to RT, where R is the gas constant. If the 3 state variables, that is pressure, volume, temperature, any 2 variables are specified, the third variable is automatically fixed. That means pressure and temperature are specified. The value of volume is fixed automatically and can be calculated from the equation of state, that is PV is equal to RT. The variables pressure and temperature, which must be necessarily specified to define the state of a system, are designated as independent state variable. The remaining state variable volume, which depends on the value of pressure and temperature, is called dependent state variable. An important characteristics of a state variable is that when a state of a system is altered, the change in the variable depends on the initial and final state of the system. For example, if we heat a sample of water from 0 degree centigrade to 25 degree centigrade, a change in temperature is equal to the difference between final and initial temperature. That is, delta T is equal to temperature final minus temperature initial, that is equal to 25 degree. because initial temperature is 0 degree centigrade, final temperature is 25 degree centigrade. So, 25 minus 0 is equal to 25 degree centigrade. The way in which the temperature change is brought about has no effect on the result. Now, let us see equilibrium and non-equilibrium states in thermodynamics. A system in which the state variables have constant values throughout the system is said to be in a state of thermodynamic equilibrium. Suppose we have a gas confined in a cylinder that has a fractionless piston. If the piston is stationary, the state of the gas can be specified by giving the values of pressure and volume. The system is then in a state of equilibrium. A system in which the state variables have different values in different parts of the system is said to be non-equilibrium state. If a gas contained in a cylinder, as stated above, is compressed very rapidly by moving down the piston, it passes through the states in which the pressure and the temperature cannot be specified. Since these properties vary throughout the gas near the piston is compressed and heated, and that at the far end of the cylinder is not. The gas then would be said to be at non-equilibrium state. Thermodynamics is concerned only with equilibrium states. So, what are the conditions for an equilibrium? First one, the temperature of the system must be uniform and must be the same as the temperature of the surroundings. That means thermal equilibrium between system and surroundings. The second one, the mechanical properties must be uniform throughout the system. That is, in a mechanical properties of system and surroundings is the equilibrium same. That is, no mechanical work is done by one part of the system on any part of the system. The third one, the chemical composition of the system must be uniform with no net chemical change, that the chemical equilibria exist. If the system is heterogeneous, a state variables of each phase remain constant in each phase. Now let us see thermodynamic process. When a thermodynamic system changes from one state to another, the operation is called as process. This process involves change of the conditions, temperature, pressure, volume. The various types of thermodynamic process are there: isothermal process, isobaric process, isochoric process, adiabatic process, cyclic process. First, let us see isothermal process. Those processes in which the temperature remains fixed are termed as isothermal process. It is often achieved by placing the system in a thermostat. Thermostat means that at a constant water temperature bath. For an isothermal process, dT is equal to 0. Next, let us see adiabatic process. Those processes in which no heat can flow into or out of the system are called adiabatic process. Adiabatic conditions can be approached by carrying the process in an insulated container such as thermoflask. High vacuum and highly polished surfaces help to achieve thermal insulation. For an adiabatic process, dQ is equal to 0. Third one is isobaric process. Those processes which takes place at a constant pressure are called isobaric process. For example, heating of water to its boiling point and its vaporization takes place at the same atmospheric pressure. These changes are therefore designated as isobaric process or said to be take place isobarically. That means isobaric process dP is equal to 0. The fourth one is the isochoric process. In this process, the volume remains constant. That is known as the isochoric process. The heating of a substance in a non-expanding chamber is an example for isochoric process. dV is equal to 0 for the isochoric process. The fifth one is the cyclic process. When a system in a given state goes through a number of different processes and finally returns to its initial state, the overall process is known as a cyclic process. For a cyclic process, dE is equal to 0 and dH is equal to 0. That is, change in enthalpy, change in internal energy is constant, that is equal to 0. The next we see for reversible and irreversible process of a thermodynamic system. A thermodynamic reverse process is one that takes place very small and its direction at any point can be reversed by a very small change in the state of the system. In fact, a reversible process is considered to proceed from the initial state to the final state through a infinity series of small stages. At initial and final and all intermediate stages, the system in an equilibrium state. This is so because small changes in the state of the system at each intermediate step is negligible. When a process goes from initial to final state in a single step and cannot be carried in the reverse order, it is said to be an irreversible process. Here the system is an equilibrium state in the beginning and the end, but not at points in between. Consider a certain quantity of a gas contained in a cylinder having a weightless and frictionless piston. The expansion of gas can be carried by two methods illustrated. Let the pressure applied to the piston be P, and this is equal to the internal pressure of the gas. Since the external and internal pressure are exactly counterbalanced, the piston remains stationary and there is no change in volume of the gas. Now, suppose the pressure of the piston is decreased by a small amount dP, thus the external pressure of the piston being P minus dP. The piston moves up and the gas will expand by a very small amount. The gas will therefore be expanded very slowly by a thermodynamically reversible process. The gas will therefore be expanded very slowly by a thermodynamically reversible process. At all stages in the expansion of a gas, dP being negligible, small the gas is maintained in a state of the equilibrium throughout. If at any point of the process the pressure is increased by dP, the gas would contract reversibly. On the other hand, the expansion is irreversible if the pressure on a piston is decreased suddenly. It moves upward rapidly in a single operation. The gas is in equilibrium state in the initial and the final stages only. The expansion of a gas in this case takes place in an irreversible manner. Now let us see the difference between reversible and irreversible process. Reversible process takes place in infinity number of small steps and it would take infinity time to occur. But in irreversible process, it takes place infinity time. Reversible process is an imaginary as it assumes the presence of fractionless and weightless piston. Irreversible process, it is real and can be performed actually. Reversible process is an equilibrium state at all stages of the operation. Irreversible process or equilibrium state only at the initial and final stages of the operation. Reversible process, all changes are reversed when the process is carried out in reversible direction. Irreversible process, type of process or occurred, all changes do not return to the initial state by themselves. Reversible process is extremely slow. It produced at measurable speed. Irreversible process is work done by the reversible process is greater than the corresponding irreversible process. Work done by an irreversible process is smaller than the corresponding reversible process. In this module, we learned about the definition, scope and the limitations of thermodynamics, basic concepts and types of the system, properties and the process of the thermodynamic terms. Thank you.